Here's a common misconception. Here's a common misconception is that objects in which there is no net force are always at rest. So if I restate that, it's not true to assume that if there's no net force on an object that it is at rest. It could be at rest, but it could also be moving. Look at Newton's first law. An object at rest stays at rest. An object in motion stays in motion unless acted on by a net external force that's not zero. So if an object's already moving and you have no forces acting on it, or the net force is zero, it's going to continue to move. Okay? So if I had, this is why like when you hit a hockey puck on ice, it tends to stay moving longer because the friction force is much smaller. But if I removed all friction in that context, what would that puck do?
Keep going.
It would keep moving forever until it hit something. Or, yeah, you get what I'm saying. I know, it's really weird to think because, guys, there's forces everywhere in this world and we don't really experience that ever. Okay, but it is true. Let me show you what I mean. When you set your cruise, okay, on your car, and you're traveling at constant velocity, you have a net force of zero on your car, assuming wind isn't changing. Okay? So, we're going to talk about the two situations where a net force of zero could mean one thing in one situation and another thing in a different situation. Okay, let me show you. Or write this. Okay? When your F net equals zero. This is what is always true. When you have no net force, you are not accelerating. But there are two situations where you've got no acceleration. The first is at rest. You're not accelerating at rest, correct? What is the second situation?
Force is constant.
Constant what?
Local loss.
This is really important. You're going to want to write this in. Yes, it is hard to imagine. Okay, but think of terminal velocity. Do we know what terminal velocity? That I refused for physical science. It's been a while. So terminal velocity, when you drop an object, it gets faster and faster and faster, right? Because it's accelerating due to gravity. Well, as it gets faster, what increases other than its speed? Drag, or the air resistance. Okay? So when you first drop an object, your force is gravity and gravity alone. Okay? As you get faster and faster, your drag force starts to get bigger and bigger and bigger and bigger because you're displacing more and more air every second. Until what happens? Those two forces are equal. Does this mean the object's not falling?
No.
It's just not falling faster and faster. It's falling at a constant velocity. That is what is called terminal velocity. So yes, there is a point where an object will stop speeding up when you drop it. Doesn't mean it stops, it just stops speeding up. It stops accelerating. And travels at the same constant velocity the remainder of the path until it hits the ground.
Yeah, does that mean that there's like a speed cap on everything?
Yeah. Well, in free fall. If I were in a vacuum, it would continue to accelerate to infinity. Does that make sense? Because there's no air resistance to ever balance out the gravitational force. Does that make sense?
Something starts accelerating too much. Like, could it
In
burn
air
up?
resistance, that's how meters run up.
I mean, like,
I get burned up, but like.
it would be more because the force was too strong, right? Because like the force causes an acceleration. So like, if you know, hit something really quickly and it was something brittle, it wouldn't be able to withstand that force and it would break. I think we'll look at it better that way than accelerating too fast. Does that make sense?
Yeah.
All right. So. Newton's first law is referring to net force, and what we're going to be doing in this chapter is we're going to have multiple forces. We're going to add those forces like we added vectors last chapter, and we're going to figure out the vector sum of all of our forces to figure out what's going to happen on an object that has multiple forces acting on it. Okay? The net force of an object can be found using the method of finding resultant vectors from last chapter. Although several forces are acting on this car, the vector sum of the forces, or the net force, is what? Zero. Thus, the net force is that, and the car moves at constant velocity. So, this resistant force is really made up of two things. What would it, in reality, what is it made up
Air
of?
resistance.
Friction and air resistance. Okay?
What's that?
There's not a lot of force.
That would be the engine spinning the cars, tires, propelling it forward.
That's not like realistic though, right?
What do you mean?
Like in real life when you're driving, your resistance backwards.
Isn't constant, yeah. Like the friction is fairly constant, but even you could even make the argument that each slab of road has a slightly different friction to it. Do you see what I'm saying? And as you progress, can wind change and change directions? You see why we ignore air resistance?
Yeah.
And to a lesser extent, friction, because it's much more difficult. Now, if you get to a higher level and go on to a much higher physics level, will you potentially have to do that? Yes. The only thing that I don't teach you that I learned in college was there was a small chapter on calculating air resistance, and it was very difficult. And I had no physics background at all. I never took a high school physics class. So like. Yeah. Okay. Yes. Progressive. Inertia. You guys should be.
Inertia.
Okay. Shush. Okay. So inertia, really, really important. Inertia goes so. I mean, the reason why. I don't know. You may or may not have heard this. A lot of times, the first law, Newton's first law, is referred to as the law of inertia. Okay? And the reason why is essentially what inertia is it's an object's ability to resist movement. Or an object's desire to continue doing what it's doing. Does that make sense? Okay? So if an object's at rest, it wants to continue doing that. And so it will resist moving. If an object is moving, it will try to continue moving. Okay? Now, inertia and mass are really closely related. The more massive the object is, the harder it is to change its motion. You guys will experience this when you try to push a heavy object versus a small object. Or like when you were kids and you made snowman, it was a lot more difficult to push a snowball as it got bigger, right? Yeah, right? I mean, maybe you guys maybe you guys sat and watched TV all day. Probably what you guys did.
What is that? That's actually
Yeah, well, I'm saying, like, we used to make snowmen like the base was like that big.
Yeah, one time
I know that's
we made a middle
My
section.
brother and I would like push together to try to, because I got to the point where I couldn't push it myself, and so we pushed together to try to continue to roll.
Teamwork. One time we made a middle
Yeah.
section that was so big we had to get like a board to roll it up.
Yeah,
and get on.
yeah. Okay, and here's the thing, right? If you walk out and try to push the car, it would be hard to do, right? Okay, much more difficult than pushing, a ping pong ball. I mean, that's not a great example, but I can't think of something else. Okay? So it's very, very closely related to mass. You guys exhibit inertia every time you're driving in a vehicle and someone turns quickly or even a little bit, you notice it. What do I mean by that?
You slide.
Right? So like if I don't want to draw pictures, I'm just bad at it and it ends up turning into something inappropriate. So imagine driving in a car, right? When you turn left, you tend to move what? You tend to feel like you're moving right.
Turn hard enough.
Okay? And really what's happening, guys, is inertia setting in. Your body wants to continue going straight. Okay? And it would continue going straight unless you hit the seat buckle or you hit the side of the car or whatever. Something forced you to follow. Or lean. But that's still a force on your body's applying a force to do that, right?
So it's not your brain.
What? It's not your brain. Guys, if you slam on the brakes without your seat buckle, what happens? You fly forward. Right, that's the same idea. And you would continue flying forward if you didn't hit the windshield, right? Or, you know what I'm saying? That is inertia right there. Stop.
It's a patch with Performance episode where they're doing a go-kart lap, and they say it's because of your brain, not inertia. Like, it's your brain that tells you that you want to keep going and not inertia. And I was like, that's a total lie, because groceries will slide around.
Yeah, because the 3-year-old Cole watching the Fashion Show.
I remember that episode.
I prove it.
This is so good.
So I would
I'm gonna skip this.
I'm moving
Yeah, equilibrium. Last thing before we get to some problems. A lot of times we will say net force of 0 would also be like saying you're at equilibrium. Okay, so there's a couple things. If I say net force is 0, you could say I'm at equilibrium. You could say I'm at rest. You could say I'm moving at constant velocity. All those things could be a possibility. Now, saying you're at equilibrium would be correct whether you're at rest or constant velocity.
That's a test.
Assuming
Write that one down.
Assuming what?
assuming net force is 0.
That's a true false.
Yeah, if net force is 0, always equilibrium. Always. If net force is not 0, never at equilibrium. Always. But this is not an always statement. And this is not an always statement. Does that make sense? If I'm at a net force of 0, I cannot say I am always at rest. Because I could be moving at constant velocity. But I can say I'm at equilibrium.
Always.
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 Always. Why are you always at a time?
No, always.
Well, when the net force is 0.
It's like brain rat feeling. My brain.
Well, you're at equilibrium.
Derek.
Derek, you're so Derek.
That's how.
Hey, Eric Merrifield got 1 of 200% on my physical science quiz.
I used to
So he
just-
didn't.
200?
Alright. This problem stinks, so pay attention. Alright, Derek leaves a physics book on top of a drafting table that is inclined at 35 degrees. So here's our table. Okay, let's say that this is the x-axis.
The x-axis.
This is the y-axis.
Oh, man.
Wait, so
That gives me
if it says it's inclined at 35 degrees, why is it going down?
Because the drafting table is like,
I agree, visualizing it, it seems like,
Okay.
but if it's inclined, it seems like.
I also think it will.
Doesn't actually.
Okay, there's your 35-degree table. We got a what on it?
A book. Physics book.
We'll say the point mass there is like that.
Like 3-rod diagram.
Let's try to figure out the 3-by diagram before we figure out net force here.
I mean, it should show us.
Okay? Let's figure out what's going to be acting on. What do we know is going to be acting on?
Gravity.
Okay, so
The force of.
gravity is going to be straight down, correct? Always?
Yes.
We'll say FG. Did they tell us what that is or anything like that? No.
And then won't there be a force of the
Okay, they should have.
Yes, there's.
Okay, I'm gonna write what it is. 22 newtons. Right? What other force would be acting on it?
Friction pushing us.
Okay, the normal force, which is perpendicular to the surface. What would be the surface in this case?
So the X
This
axis
right here.
of the table.
That's your table. That would be perpendicular. That's how it would be pushing. So it would be pushing perpendicular to that surface. That's your normal force. And I'll tell you what that is. That's going to be 18 newtons. At the end of this chapter, they'll give us one of the four forces. We have to find all of the four forces and then find the net force and then find how much it accelerates. Okay, so just, we're starting simple. What else?
Friction.
Wait, we don't do that.
No, I think you
No, we're doing it.
You have to.
Friction always resists motion. Okay, let's say the friction force is, this is gonna fall that way, right? So friction would resist its motion. We'll say 11 newtons.
And then as the.
Find the net force acting on the book. Hoof to doofta.
That'd be funny if I actually don't.
Does
know.
it have a force going to the right, or is that encompassed in the normal force? Or is that what you're
It's gonna
finding?
be going to the right because the x component of this is gonna be greater than that. I'll just tell you.
What is F? What's FG?
Force of gravity. Okay. We'll talk about this. Now this becomes difficult. As of right now, how I have it set up, what is the only force that's on, specifically on the x or y axis?
Gravity.
Gravity is the only one. But if my x or y axis was arranged like that, I would have two that were on there.
That would just make it one.
No, it won't. I promise it'll make it more easy. What?
All
The two what? Two forces? That force, that force? Okay, so let me show you. I'm going to take this and tilt it. Here's why. Now listen, I'm going to take it and I'm going to drop it, but think of it. We're just shifting everything 35 degrees. Okay, so I'm going to say my force, well, friction's now on the x. My normal force is straight up. 11. And my gravity will have shifted that way, right? 35 degrees.
So that would mean.
But which angle is it? Is it this angle?
It's the close.
Or is it this angle?
West.
Bottom,
No,
east to
it's
south,
east
east to south.
East to south.
Yeah.
Be this angle.
Or alternatively.
Everyone see how that worked? It's a little bit tricky, you gotta think a little bit. I'm taking this and I'm shifting it down so that this is on the x, this is on the y, and this now is straight down, shifted 35 degrees that way.
Why did you choose this?
Well, because assuming like if I were to draw like an actual x, y like right here, you see how like when I shifted it 35 degrees it would be that angle, not the other angle.
You can find the components.
Mr. Kramer.
Yeah, you can find the components.
Mr. Kramer.
What?
Explain the 35 degree thing.
22 sin.
Yeah, I'm lost. He just shifted it, see how it's.
So I took this and I shifted it down. Well, everything's rotating that way. Does that make sense? Like that's how I'm rotating everything. I'm taking it and I'm spinning it. Well, I'm spinning it so that, right, imagine if I take away this ramp. That's going to be straight west, that's going to be straight north, and if I take away the ramp, this is going to shift 35 degrees that way.
Why did they shift that other way then? I was shifting that way.
If I take this, that's straight up, and I shift it this way, right?
Yeah.
Make that one.
Oh, just kidding.
I could say, I could use this angle,
Never mind, I
and
was
it'd be 55.
Okay.
Okay, another way of looking at that would be, if this is 35, this is a right triangle here. So technically, this angle would be 55.
That's
You can use either, doesn't matter.
55 south.
It doesn't matter which one you use, just know if you use this one, your opposite is X. If you use this angle, your opposite is Y. Now listen, here's what we're doing. We need to find the net force. So we know this is all X, this is all Y. This needs to be broken up into a X and Y.
Yeah,
So F, Y, G. F, X, G. Do you see what I did?
yeah.
It's the gravity of the force of gravity in the X component, Y component. So if I use the 35 degrees, which is what I'm going to use here, so I'm going to get rid of the 55 so I don't confuse you. My opposite is X, correct? So your FG would be, what did I say this was, 22? 22, opposite would be sine of 35.
Which is 12.62.
Just put 12.6, is that cool?
Yeah, that's good. But then that's gonna mess. Well, kind of.
Okay, your f of y would be 22 cosine of 35, which would be what? It's what? 18. And thankfully it is, because look at that.
Gross. I don't like
That's so not.
Okay, now stop. Now listen, here's what's happening here. Now technically this would be a positive or a negative,
Negative.
right? That's a downward force, correct?
Uh-huh.
Yeah.
Okay, so let's do Fx total and Fy total. My y would be a positive 18 minus a negative 18. Sorry, plus a negative 18. Yeah, sorry.
Otherwise that would be.
My x would be, is this x a positive x or negative?
Positive.
Positive, so 12.6 newtons
Plus negative 11.
plus a negative 11 or minus
Oh my goodness.
11 is 1.6 newtons.
So it's.
So you
Oh,
said
why does-
1.6.
Now,
18 newtons minus.
now, you don't get confused. Before I go back and give a direction, I need to go and shift this back up. Because this x from the original context is that direction, which is down the slope. So we're not actually going straight x and it's all of a sudden levitating off the ground of the, does that make sense? Okay, so we would take this, shift it back up when I give my direction. Okay? And since this is right on the slope, I would just say it's traveling 1.6 newtons down the table.
You can't say traveling in newtons, can you?
Well, what direction? What if we gave a direction?
Well, in this case, you could say what? You could say 55 degrees.
So you want us to just say
West
down
of
the
north.
It's not 35, okay.
I would just base it off what that table is. Because we know, guys, from common sense, we know that this book is traveling down the incline.
So south.
So is it 1.6 down table?
Yeah, you probably should say south.
You know how like you see
Okay? Because technically this is going to go.
Yeah, like that. I don't want to tell them.
It's going south, it's not going north.
If you make a little.
And then I woke up, I was
Let me stop it.
Oh, yeah.
You can do that. Yeah, it's a different angle.
sleeping in, so I set an alarm.
You have to put that as 1.6 newtons down the table.
Yeah.
This morning, I was like, so you, before you said.
It would either be 55 south of east or 35 south.
Like usually I sit on the couch and it gets bright in there. Oh, no, man. I get up, but.
Oh, you guys need to have your